All right, so we're continuing. Oops. We're continuing 2.3, the limit laws. And so far we've talked about the sum laws, constant times the function laws. We talked about taking the limit of a fraction, right? And the limit of a product. Okay. Um, and now you'll notice that when we have nice functions like polynomials or rational functions, remember that a rational function is a polynomial divided by a polynomial. Then we have a new, we're going to write down a theorem. If f is a polynomial or a rational function, then take the limit as x approaches a of f of x, what do? We simply plug the value of a in, provided a is in the domain of f. Now, what does this restriction mean? For example, here, if I were going, instead of going to 2, if I had changed that to a -3, then I would not have been able to say this is 4 minus 1 over 0, right? Because that's not in the domain of this function. I can't, the point that makes the denominator 0 would not be in the domain of f. Okay, so now this theorem tells us if I have a polynomial or a rational function, it's really easy to compute the limit. I can compute the limit by plugging things in. All right. So now continuing with that, another theorem, theorem 2, say, we're going to have lots of theorems. If I'm taking the limit as x approaches a of, well, maybe I should stop here for a second. I need to set that up a little bit better. If f of x is less than or equal to g of x, when x is near a, except possibly at x equals a, right? Because the limit doesn't matter. Then I'm just going to take the limit of both sides. The limit as x approaches a of f of x is going to be less than or equal to the limit as x approaches a of g of x. Okay. There's another theorem that I think I'm going to wait on for a bit. We're going to do this later. I'm going to introduce it now because if you're reading in the book, they're going to pop it out here. Later is going to be a theorem called the squeeze theorem. But I think I'm going to wait on the squeeze theorem until our next video. This one will be more algebraic. So let's try a few limits, examples, because now we just want to compute a bunch of limits. Find the limit as x approaches 2 of the square root of x squared plus 3x divided by x squared plus 2x plus 1. Okay, how am I going to get that limit? Well, you'll notice that if you plug in 2, right, you get 4 plus 4 plus 1 is 5, and then 4 plus 6 is 10 on the top. And so this is in the point in the domain. And while this isn't a polynomial like we had in the last page, it is a well-behaved function. And so formally we can write that as the square root of the limit. In fact, we can go ahead and bring the limit in. X approaches 2 of the x squared plus 3x, and then the x squared plus 2x plus 1. And this is true by the limit laws that we looked at in the last video. So now these are polynomials, and you can see that now you can just plug things in as long as your denominator is not 0. And so we just get 4 plus 6 divided by 4 plus 4 plus 1. Good. So square root of 10 ninths. Okay, how about the next one will be the limit as x approaches 2. How about negative 2? Just to make it more complicated, 2 minus the absolute value of x divided by 2 plus x. Okay. Well, we run into two problems right off the bat, right? One problem is I can't stick in the negative 2 because the denominator would be 0. The other problem is that if I try to put in x equals minus 2 in the numerator, I also get a 0. I wonder how that's going to work. Here's a hint. Whenever you're dealing with the absolute value, we want to get rid of it by rewriting the expression. So 2 minus the absolute value of x divided by 2 plus x is equal to one of two expressions depending on x. So for example, in the first case, if x is greater than 0, greater than or equal to 0, right, then how does this simplify? This expression becomes 2 minus x divided by 2 plus x. Okay, then what happens if x is less than 0? Then the numerator becomes 2 minus x, right? Or 2 plus x divided by 2 plus x. Oops. Oh, that's interesting because that cancels each other out, and that's just 1. Okay, so on the graph, right, if x is negative, my function is just the function 1 on the negative side. And then it would be undefined here. I guess I should be careful because at x equals minus 2, the function is also not defined, so I should put an empty circle there. Okay, and then on this side, you could graph this function, 2 minus x over 2 plus x, but it's not going to be relevant, right? Because all we're interested in is what happens at x as x goes to minus 2. So you can see here, as x goes to minus 2 from the left or the right, the limit is equal to 1. Good. All right, so you could tell that. You didn't have to use the graph. As soon as you get to the algebraic definition here, I think you see that it's equal to 1. Good, that was a tough one. Let's try another one. I have to change pages on you here. How about the limit as x approaches 4 of x squared minus 4x divided by x squared minus 3x minus 4. Now, if I try to put 4 into the denominator, what do I get? 4 squared is going to be 16. 3 times 4 is 12. So that's minus 12, and minus 4 is minus 16. I get a 0 in the denominator. So I can't just plug 4 into the numerator and denominator in this case. So I have to do more work to figure out the limit. And so what you're probably suspecting is that these polynomials here factor. And so before we actually take the limit, we want to factor and cancel if possible. X minus 4. And then what are the factors down below? Here's a hint. If x equals 4 makes the polynomial equal to 0, then x minus 4 is going to be one of the factors. It's just a way of getting to be fast when you're computing these. So therefore, what's the other factor got to be? I believe it's going to have to be plus 1, right? So then we get a minus 4 for that, and then a minus 4x plus x will give us a minus 3x. Very good. And what do we see here? We can cancel out the bad point. And so now we can plug in our x equals 4 here. And so that would be a 4 in the numerator and a 4 plus 1 in the denominator. Good. So therefore, the limit exists. Very good. So again, this was when I tried to look at this initially. Remember that I had a 0 divided by 0, and so that was kind of the key to factoring first. Now suppose that I had changed the problem. Suppose I had the limit as x approaches 4 of 1 over x squared minus 3x minus 4. Then notice that as you approach 4, what happens in the denominator? The denominator is going to 0, and so we don't get 0 over 0 in that case. We get that this is going to go to 1 over 0. Now, remember from our work with our fractions, how would you interpret this answer? Having the denominator go to 0 but the numerator not means that overall the fraction is blowing up, because these numbers are getting like 1/10, 1 over 100, 1 over 1,000. So 1 over those numbers are getting huge. It's going to plus or minus infinity, so it does not exist. Okay, so it's kind of important to check to see where your limit is going before you actually start. And I see that I'm up for time in this one. In our next example, or in our next video, we'll probably do more examples, and then we'll get that last theorem in, the squeeze theorem. See you there.